Okay, let's go on to subtopic 2.3, which is on capacitors with dielectrics. In this subtopic, you should be able to define dielectric constant, describe the effect of dielectric on a parallel plate capacitor, use dielectric constant, and lastly, use capacitance with dielectric. Okay, so this is a parallel plate capacitor. So let's consider this metallic plate. So it has equal area and are separated by a distance d, and the space between the plates is either vacuum ataupun air lah. Okay, so when the capacitor is charged, this plate will have charges of equal magnitude but opposite sign. So if this part here is positive, the charge on the opposite plate will be a negative terminal lah. Okay, so due to this different terminal, it produces a potential difference across the plates, which is somewhere around here lah. Okay, so this is the potential difference produced by the positive and negative terminal. And since the distance here is much more less than the area, the electric field strength can be called uniform lah. Okay, so the electric field strength here is uniform. So the magnitude of electric field can be calculated by this formula given here, and then this sigma here is known as the surface charge density, and the unit is coulomb per meter square, and it is a scalar quantity lah. Okay, and since Q is equal to CV, we can write down NV is equal to ED here. This is only valid for uniform electric field strength. So the equation here can also be written as this one here. Okay, so you can either use this equation here ataupun yang inilah di bawah. Okay, so this capacitor can either be separated by a vacuum ataupun by a dielectric material lah. Okay, so for a capacitor being separated by a vacuum, the epsilon naught here is the permittivity of free space. Okay, the permittivity of free space is the value is this one lah. Okay, and if it is separated by a dielectric material, it depends on the type of material. Okay, so from these two equations, the capacitance of a parallel plate capacitor is basically proportional to the area. Okay, so what we can write is capacitance is proportional to the area of the plates and inversely proportional to the plate separation. Okay, so if the area of the capacitor is bigger, then the capacitance is also greater lah. Okay, this one vice versa lah. Alright, so let's move on. So what is the effect of a dielectric material on a parallel plate capacitor? So basically this diagram here is explaining what is happening when you are inserting a dielectric material lah. So if you don't have any dielectric material between the plates of the capacitor, the plates are separated by a vacuum lah. So when it is connected to a battery, it will give charge on the plates. So this would become a positive terminal, and this one will become a negative terminal. So when the battery is removed, the charge on the plate will remain constant. Okay, so the electric field between the plates will be uniform and has a magnitude of E naught. So E naught meaning it is the initial electric field strength lah. Okay, so the separation is constant, which is known as D. When a dielectric is placed, so when we are inserting this dielectric here, the electric field between the electric field in the plates, the molecules will become oriented with their positive ends pointing towards the negatively charged, and then their negative ends pula will be pointing towards the positively charged plate lah. Okay, and itu kamu boleh tengok di sini. Okay, so this negative will be attracted to the positive terminal, and then for the positive end of the dielectric material, it will be attracted to the negative terminal. Okay, so this result is a built up of positive charge lah. The result is a build-up of positive charge on one surface and a negative charge on the other. Okay, and then the number of field lines within the dielectric is reduced, hence the electric field is partially cancelled. Okay, so what is happening is when the dielectric material is inserted, the electric field strength is less than the original electric field strength. Okay, so because of that, the potential difference across the plate would also reduce lah. Why? Because electric field strength is directly proportional to the potential difference. Okay, so and since the potential difference is smaller and the charge remains the same, the capacitance will increase. Okay, so that is the effect of a dielectric material being placed in between the plates of a capacitor lah. Okay, so make sure you understand the factor, the effect of putting a dielectric material lah. So basically, mainly what it does is it increases the capacitance. Okay, right, so that is on dielectric material. Now we are focusing on dielectric constant. Okay, so it is, the symbol is epsilon r ataupun this one. Okay, so it is defined as a ratio between the capacitance width of a given capacitor with space between plates filled with dielectric and the capacitance of the same capacitor with plates in a vacuum. So basically the ratio between capacitance that has dielectric but with air, and then with dielectric yang have capacitance with dielectric material lah. Okay, and then it has no unit. And then for parallel plates capacitor, you can actually relate this dielectric constant to the permittivity of free space and permittivity of a dielectric material lah. Okay, and then from the definition of capacitance, we can also obtain that dielectric constant is the ratio of the initial voltage, potential difference across capacitor with dielectric, in vacuum, and then over the dielectric lah. Okay, and then we can also relate this between electric field. So the equation can also be written as this one. So basically kalau dia ada note di bawah, E note begini, maksud dia it is in vacuum. Okay, it is in vacuum, capacitor in vacuum, whereas the one yang tiada tu, it is capacitor with dielectric material. Okay, so the dielectric constant depends on the insulating material used. So basically this table is showing you the dielectric constant for several types of material. Okay, and then the dielectric strength here is defined as the electric field strength at which the dielectric breakdown occurs and the material becomes a conductor. Okay, so this is the summarization of the formula you can use to find dielectric constant. Okay, alright, so that is basically the theory part for our final subtopic in this chapter.